So thanks. I think this will actually be a pretty much shorter than the time allotted, I hope, because what I aim for is to give you a bird's eye view of the options and of the questions and the options you have when you think of using a neural generative model. So first of all, what does that even mean, generative? So is a model that outputs a simple number generative? Probably not. What if a model chooses one option out of 10? Well, hardly. One option out of a billion? Probably. But so I mean by generative models here, I will just mean models whose output spans a pretty large universe. So it's clear that it's a spectrum between things that are generative and things that are not. So the first question, that you have to face when you think of using a generative model is, do you actually need one for your problem? Because all of these things, they're reasonably tricky and require a reasonable time investment. And so if you can get away without using one, you should. Like, if it's possible, always go for the stupid option. For example, if you want a chatbot, then quite likely just a simple, straight-up, explicit algorithm that just selects one of 10 possible templates, and then equally with explicit rules, fills the blanks in the templates. Will do just fine. And in fact, for some of our natural language generation tasks, this has worked great. So in some cases, so if you can get away without using complex things, do. And by the way, if you just want to have a simple regression, simple classification task, I could recommend extreme gradient boosting that has pretty consistently beating neural models for simple classification regression tasks in our practice. And there is a nice Python library for this, and our library, I think, as well. So that should be the first protocol. If that's not good enough, and you still want something complex, then what you need to understand is the structure of your problem. What are the important options? The first one is, what's the structure of your output space? What are you trying to produce? And here, the big distinction is something continuous. So basically, some kind of an n-dimensional array of real numbers. Images, audio, that sort of thing. And that's actually the easier option. The other one, which is more interesting, is if your output space is discrete. And discrete, again, can come in many shapes. The most common one, perhaps, is text, or things that form a linear sequence. But also, for example, a series of button presses to win a computer game it can be looked at as a generative task. You produce a sequence. And that also is a linear sequence. But again, not all discrete problems are linear. Some of them have another structure. The second most frequent structure, perhaps, is a graph. So you have connections, and possibly different kinds of connections, and possibly inference on those, so it's a knowledge graph. But in any case, the connections, it's not just a line. And so the structure of the output space is really the important thing. For the inputs, it's not as crucial for choosing your approach, as we'll see further in. The second big question is, do you have an objective function? And that is really perhaps the second major determinant of what you go for. Again, because the neural networks, their native language is continuous variables. If you have a continuous objective function, your life is good. The other option is you have a discrete valued objective function, so for example, in natural language understanding, your model produces an answer, and your objective function tells you, is this the right answer, or is this the wrong answer? So then the function is explicit. You have a black box that gives you a valuation, but it's discrete. And then finally, a most frequent and interesting case, of course, is when you have just a set of examples. Either just a set of, for example, images, and you want to produce more images like that, whatever that means. Or a set of input-output pairs, for example, for machine translation. So once you have those two questions, you need to decide based on this what model structure to go for. And here, I deliberately take a very high bird's eye view, and we'll try to, just so we didn't get lost in the details. And then we'll be more than happy to drill into any of the details once, in the questions time. So basically, in the generative models, there are three major optimization patterns. And of course, none of it is exclusive, because all these areas have been exploding, so there are exceptions to any general statement about any of one of those areas. But I'm just trying to cover, if I had to solve a problem in this domain, what would be my first port of call? And the first one, perhaps the most powerful, is encoder-decoder. There you have, again, two flavors. So how do encoder-decoders work? You take a bunch of real-world inputs with whatever structure they have, and you have an encoder which turns each input into either a vector or a variable length sequence of vectors. So the big distinction here is it a fixed dimensional encoded output, or is the output variable dimension? So let's look at fixed dimension, which essentially is equivalent to a vector. You want to use that if you want to summarize your inputs in some way. So a particular case here is autoencoders, where input and output should be the same. So then the decoder part is you take that vector you've just encoded, and you try to produce the output you want from that using the second network called the decoder. And you train them together. So you have input-output pairs. For the autoencoder, the input is the same as the output. And then encoder transforms it into some kind of an internal vector. Decoder tries to transform it back. And what is that good for? Well, generally what that achieves is that by squeezing all the information in a complex initial outputs through that little vector, that forces the networks to encode the features that matter for reconstructing the input efficiently. So then once you have trained this kind of an encoder-decoder pair, then one thing people have done in a bunch of domains, last talk I heard was on astronomic object classification, was you can do clustering in what is called the latent space. So this space of the vector into which the encoder maps your inputs, that's called the latent space. And in that latent space, then you can do clustering in a much nicer fashion, because by squeezing your complex input into that tiny vector, the network is forced to encode the features that matter. And then you can do clustering in that space. The other nice thing about this is that then you can sample from that space. So you don't, once you have the latent space, you don't need to use the encoder. You can just take a random vector from the latent space, apply the decoder, and get back your output object. So this is a nice pattern. However, in some cases, that one vector proves to be too small or too simple a structure to squeeze all the information into. So then the second equally popular version is an encoder-decoder where the encoded state is a variable length sequence. So you see this a lot, for example, in natural language translation, where what you do, an encoder just takes a set of tokens, which so you translate, you convert your input text into a series of tokens using your favorite algorithms. So the tokens could be words, they could be individual characters, they could be byte pair encoding, whatever you like. And then you transform each token into one vector in your encoded sequence. And then the decoder, rather than taking the single latent space vector as an input, it takes the sequence, and at each step, it applies weights using some kind of attention mechanism to get the averaged weight, attention weight average vector for this decoder step, and then repeats. So this way you can smuggle more information through, and which means you get better translations, for example, but at the same time, it's less useful for sampling from, because how can you sample from a variable length sequence? You could do it, but it's just messy. The next one, which has perhaps been the most famous one, are the generative adversarial networks, GANs. And here you actually use almost the same building blocks as for autoencoders, but you put them together in a different way. So first, you have a generator model, which usually can be exactly the same or very much the same architecture as your decoder, which just takes a vector as an input and produces something in a target space. And then you have a discriminator, which tries to tell, is this particular output, say this image, was it produced by the generator or was it a real image? And then you train the two models in tandem. So you train the discriminator to distinguish, and you train the generator to fool the discriminator. Now, in the world of image generation, this has achieved spectacular successes. But one big practical downside is that these things are notoriously hard to train. So the training can be, because there is no such thing as a global optimum, because you're trying to, the two networks are competing. And so while the payoff is potentially good, this is the path that is perhaps the most tricky. However, the upside here is that all it needs from you is a set of examples. Final one, which not everybody thinks of when they talk about generative models, is reinforcement learning. And basically, a broad definition of reinforcement learning could be that you could optimize an objective function, which is an outcome of many successive decisions. So the most famous one, perhaps, is the AlphaGo algorithm, and then AlphaZero its successor, which beat the world champions in the game of Go, where the target space is huge, and only at the beginning of a very long game do you know whether you won or not. And one could, and people have, held whole lecture courses about different flavors of reinforcement learning. But if you just want to dive into it, a currently popular method, which seems to work quite well, and is not terribly complex to implement, is proximate policy optimization. The one thing you do need for reinforcement learning, though, is an objective function. So you need to have a payoff at the end. You need to somehow improvise a payoff that makes sense. That is in contrast to GANs, where you just need examples. On the other hand, the upside of reinforcement learning is that you don't need examples. You can, as long as you have a payoff, your generator can produce whatever it wants, and all you need to know is the score at the end. So now we have seen two bits. We have seen the shape of our problem, and we have seen the possible patterns. The interesting part is how you go from one to the other. And let's go through through several examples. So the simplest one is you have a continuous output space and a continuous valued objective function. And this is perhaps the ideal case. So if all you want to have is to optimize your objective function, then you just create your network, plug in the objective function, run gradient descent on the result, and you're happy. Maybe you want to produce not one output that maximizes the objective function, but many. Then you could introduce some randomization into the process. But in any case, all these networks have dropout. So if you want to produce a bunch of good examples, you just do inference with dropout turned on. And you have your decent outputs. Again, of course, optimization through gradient descent is not without its pitfalls. But the same is true of all the methods here. So I'm talking like really, really big start. Now, next case, continuous output space and a discrete objective function. There, really what you want to do is to cheat a bit and to train a proxy objective function which is continuous. And here, again, the nice thing is you don't need examples as long as you have an objective function. So what you do is you start your model with random weights, you produce a bunch of examples, you score them using a discrete objective function, and then you train a continuous predictor of that objective function. And then you have two models, but unlike in the GAN case, you don't try, these options are not competing, or not necessarily. So you train your generator, and then you train your continuous objective function to approximate the scores of the true discrete one. Right, next space is we have a discrete output space with an objective function. An example which I have been playing quite a bit in my spare time lately is molecule optimization. So generally, when you work in discrete spaces, the trick people use is to turn this into a continuous problem by replacing a discrete decision. So a discrete decision is you take one of n options. What you do instead is you take a vector of probabilities of choosing any one of those options. And the probabilities are real valued, so we're back in continuous land. And so one way you could do this is you parameterize the output space in a continuous fashion. And here we come back to our autoencoders. So for example, if you have, look, one thing people have done for molecular optimization is they feed their molecule into an autoencoder, which trains to reproduce it. And then you have a latent space in the middle. And then the latent space is continuous, so you can sample from it. It's not, you cannot say what is the point halfway between this molecule and that molecule, because the space is discrete. But then when you have a mapper from point in the latent space to a molecule, you sample the latent space and optimize over the latent space. That is very nice, especially because it's a simple and general approach. So again, if in doubt, that's the first thing to try, because autoencoders are more stable to train than some of the other options. But the downside here is you assume that your latent space represents your object space well, which may or may not be true. So the other option you have here is to go directly into your target space and use a reinforcement learning approach. So any kind of a discrete space, construction of any object in a discrete space can generally be represented as a series of more or less simple options, possibly constant length, possibly variable length. For example, when you're doing molecules, then you can choose what next atom you want to attach, or what next structure you want to attach. Or if you're playing a game, which next button do you press? And then you can, if you want to work directly in that target space, then reinforcement learning is your friend. Yes, that's. Now we come into the stranger world where we don't have an objective function. So we don't technically know what we're trying to optimize. But we have examples. And then, so one perhaps most famous example here is pictures. And I think everybody probably has seen the celebrity face examples of fictional human faces, which look really nice and realistic, produced by GANs. So here again, the point is, how do you, if you don't have an objective function, how do you constrain the output of your model to the space that is similar to the examples? How do you define similar? And here the two options are, first, constrain the space from the inside, so to speak. So you train an autoencoder, and then you hope that anything that your decoder can produce, because the autoencoder has been trained this way, is now inside this latent space. And for images that didn't work well enough, so then the other option is to constrain it from the outside. So your model can produce anything, but at the end, it must satisfy, you create yourself an objective function, which is your discriminator. And then the other option is you don't have an objective function, but you have examples of not just one thing, but input-output pairs. And that's a classic encoder-decoder scenario. Right. So this is optimization style. Now the choice is how do you structure your model? What's the architecture of your model? And surprisingly enough, those choices are almost independent of the optimization style you choose. You don't always need an encoder, but you always need a decoder, though sometimes you call it the generator. And you almost always need an output transformation step. So the encoder architecture is actually the simpler choice. Because, so what's the point of encoding? The point of encoding is to turn your complicated real-life input, which can have lots of discrete features, some kind of a graph structure, some kind of pointers to other objects, who knows what, to turn it into something in the model that neural networks can work with. So either basically a fixed length vector or a variable length sequence of vectors. And then really, if your inputs are continuous, audio, video, then they're already such arrays. So then you just need to put the processing step after that. However, often you have hybrid structures. So first of all, if individual elements, so that if they're continuous, for example, they're frames in a video, or they are or they're wave patterns, then you're fine. But then sometimes it's a sequence of, for example, words, or I think words is the most frequent, is a frequent one. Then you embed them using either embeddings you train as part of your model, or you take canned ones, for example, with word embeddings. Now, often you have hybrid things, where each element is continuous, but then you have a sequence of those, which is a sequence is discrete. So if you have a sequence, put it through an RNN. If you have any kind of a continuous thing, put it through some kind of a convolutional network. And if you have a graph-like structure, you use a graph convolutional network. So really, it's usually, if you look at a particular case, the structure of the input drives the kind of embedding you choose. And then the other option, which is can sometimes be useful, is a transformer architecture, which is there was the lovely paper, Attention is All You Need. So with RNNs, you take things one step at a time and carry a state through the steps. With a transformer network, instead, each output vector is composed of a weighted average of all the input vectors, driven by attention. And so here the decision is, if you only want more or less local information. So for example, RNNs, they don't really do great for information propagation over more than a dozen steps or so in a sequence. So if your information you want to exchange between your sequence elements is more or less local, an RNN is good, or a graph convolutional network is good. If you want global information propagation, then use some kind of a global state, or use a transformer architecture. The big downside of a transformer architecture, because everything is feeding into everything, one transformer stage scales quadratically in the length of your sequence, which might or might not be a problem depending on how long your sequences are. And the other rules of thumb is use dropout liberally, and if you use more than 2 or 3 layers, use residual connections. Now the decoder architecture is where it gets more interesting. Again, for continuous outputs, it's a world of its own, but basically it's a combination of upsampling, transposed convolutions, and convolutions. For discrete outputs, the most common pattern is you do it in steps. So one discrete output is easy. You just produce a vector of probabilities for each output. But typically for discrete outputs, you need to produce a sequence. For example, you want to produce a sequence of words that is translation. And then what you do is you do it in steps. You first produce the first output in the sequence. Then you use this plus the encoded state to produce the next output, et cetera, et cetera, et cetera. And then you can either just select the highest probability each time, or you want to look several steps ahead to look for the highest cumulative probability, which is called beam search. Now here comes the most fun part, which is often underestimated, which is output transformation. Because what your neural models can typically do for you is produce a sequence of probability vectors. So for example, if you have something like text, where almost everything is possible, then that's enough, because all you have is a probability. What is the probability? What is the highest probability next word? And you select one word after another. However, in some cases, there are quite tight constraints on what is valid. For example, if your model should output a database query, there are quite tight syntax constraints on what database queries should look like. Or if your model is supposed to output a valid molecule. Well, you could train your model to learn what valid molecules look like, But I'd much rather be spending the model capacity on training what good molecules look like and make it unable to produce invalid ones. And that is where output transformation comes in. So the point of output transformation is to make life as easy as possible for your model. Basically, in the ideal case, to ensure that any choice that your model makes is a reasonable result. And then all the model has to do is to optimize between the reasonable results for the best ones. Because if you don't do that, then the model first needs to learn what's valid, or is to learn to avoid invalid or terrible results. And that's a waste of training time and model capacity. So there is a couple of tricks we can use. One, which I'm very fond of, is the use of grammars. So a grammar, you can think of a grammar as a series of templates. For example, if you have a database query, you know it's either an insert query or it's an update query. And then maybe there is a group by. And so a grammar is a series of rules where the first rule just starts from nothing and starts a template with some blanks to fill in. And each next grammar rule substitutes a particular kind of blank for another template. And so on until we're done, until there are no blanks left to fill. And so whenever you have to produce a highly structured input, such as database queries, molecules, or anything where there are additional constraints apart from the fact that it's discrete, then the grammar is your friend. And if you're producing linear sequences, then what you want is a particular kind of grammar called context-free grammar. It's probably the easiest one. And the context-free grammar just means that when you're expanding a particular token, you don't care about how you got here, you only care about what token this is. And that doesn't work for graphs. Well, you can make it work for graphs, but it's painful. But there's a very similar concept called the hypergraph replacement grammar, which does work for graphs. And the final one, which is perhaps the most fun to use, is to use an external piece of software as your input transformer. So for example, one talk at last year's ICML was somebody who had hooked up a reinforcement learning program to a graph drawing software. What the reinforcement learning model was doing is to give the coordinates of each particular brush stroke. And then the objective was, it gave you a pixelated picture, the Mona Lisa or whatever. And the model was outputting the brush strokes, which were fed into a graphics editor, which then drew the result and tried to reproduce the picture. And I think this is something which is not done very often, but can be quite powerful, because so using an external piece of software as an output transformer. Or another one is if your model actually outputs a query as an intermediate step, then you could put this query into some kind of internal engine. And then the output of the model is the result of the query. And so when you're working in discrete spaces, there are many more games you could play like this. So I could spend another hour talking about the concepts in any one of those slides probably, but I think I'd rather stop now and answer questions.
I was wondering, just go through some more examples, I guess, of how you have used some of the generative models or other practical examples you've seen.
Sure. So in my case, so I've done a lot of work in my spare time as a side project on molecular optimization. And there, what I've started with was an encoder-decoder formulation. But they're very hard to train, and you have to start from a big universe. And I wasn't happy with this. So now what I've been doing is reinforcement learning flavors for that. And reinforcement learning flavors of molecules with hypergraph grammars. Because with hypergraph grammars, you can guarantee validity of your model. So things like valences of individual atoms can be guaranteed by the grammar. But then the thing is, what is the right reinforcement learning algorithm to search over that space? Another one which is a work in progress is a voice-to-text engine for commands, where the input is just a character stream, and which can be very messy and error-prone. and the output is a series of grammar rules, which when evaluated, produce a valid command. And which makes it an easier problem than general voice to text, because you don't want to produce an English sentence, you want to produce a command from a fairly large but still limited set of commands. And the nice thing about grammar is that these things don't have to describe constant size spaces, because the grammars can be recursive, a token can expand to itself, etc. So if, for example, if you have a database query and you want to have an arbitrary number of filter statements on the end of constraints, you can express it in grammar. So I think, yeah, these are the two I've done recently.
You mentioned that you basically get output, you get basically a series of probability vectors instead.
Yep.
I was wondering whether you can sort of explore a little more how you would search this space. Like I have been searched lots of times, sort of this context, I believe, and like how and why.
Well, I think searching it in itself. Really, the only two options you have, the only three options you have is just sample the probabilities directly, and then hope something good comes out at the end statistically. Or you just choose the largest, or then you choose a beam search. And I guess the next more complicated option would be a Monte Carlo tree search, where you run a search sequence, and then you backtrack, and then you feed back the results of that particular search. And then when you run the next search sequence, then at each step you know what your previous run was like. And so you accumulate the results of all your runs in a tree, and the tree teaches you something. And then the next more convoluted step, which is how AlphaZero worked, which is at each model step, they ran a Monte Carlo tree search, they get those results, and then they train a neural network to reproduce those results. So there was a feedback loop between a neural network, which gives you the probabilities, and the Monte Carlo tree search, which refines them. But this is really computationally hungry, so unless you have a couple hundred GPUs standing by, I wouldn't necessarily go there.
I have a question. So let's say they choose a generative adversarial network and you have two classes in B.
Yeah.
And in class B, you have very few samples. How are you going to solve the problem? And you have no other sample because it's a very special type of style of thing. How are you going to using the GAN successfully to model parts of class B?
So you want to produce images from several different classes.
Yes, you have two classes and you want to kind of copy the style in class B, which is a special painter, or something particular. You have just 3 paintings to learn from. How would you do it successfully, knowing that you have such a little data in class B?
The one way I can think of is to use a semi-supervised approach. So you take a superclass, which includes both class A and class B, but which is still not too generic. And you just train your model, no matter what, to sample out of that. And then so at least your model has learned the broader enveloping class. And then you refine the model with the specific examples, so that. And then at least your model has already learned the broader class of which both pictures are members.
So the broader class is very easy to learn because it has tons of data. You have so many patents from so many artists.
Yep.
But how would you be able to copy well the style model B? Because you have, that's the problem. Even if you use a general model in the beginning from all classes, how can you say that I will copy exactly that style?
So two steps I can suggest. So first one is semi-supervised. So first you train the broader class, and then you refine. The other one is targeted enhancement of your class, because just arbitrary labeling is expensive. But what you can do is then you have techniques for estimating of these images, labeling which one would improve model discrimination ability the most. And there are techniques for doing that sort of thing. So if you have only 3 examples and that's it, then I don't have any other ideas. But if your problem is that there are not that many labeled examples and labeling is expensive, then I would use a technique like this to choose which next ones to label for the most efficiency. And people have done this for things like cancers, etc.
Yeah. Could you expand a bit on how to impose like grammar on micronormal space? Like specifically like Python, if I sound confident, like what would you show that? How would I define it? How would I use it?
So for example, a grammar would be, a grammar for database queries would be from, literal from, then non-terminal table name, literal select, and then a non-terminal field list. And then there'll be the rule number one. Rule number two was the non-terminal table name resolves to this table name. Non-terminal table name resolves to another table name. And so you have this set of rules, and then you know that if you have a non-terminal called table name in your sequence so far, then the only rule you can apply to expand it are rules where the root is table name. And so to do this with your model, you apply masking. So where you look at what you have, like you have a helper function, which is like an environment in reinforcement learning, where each time when you're choosing, what is my next non-terminal? What is my next non-terminal I'm trying to expand? And then depending on this, you generate the masks. What would be the valid expansion rules? And then you evaluate that rule. You see what the sequence looks like now. For example, the table name is evaluated. So what is the next non-terminal to expand? Next non-terminal to expand is which field I want to query for, or which column I want to query for. Then for that, you look at your next model probability vector. You know I'm looking for a field name, so you apply a mask that only rules which evaluate to a field name, or which have a field name, a non-terminal, as a root, apply like. And you iterate like this.
So do I understand right that you sort of translate the output from the original model into some other output through the grammar, and by definition, the outputs of the original model are like granted correct once transformed through the
So no, from the beginning, you train your model rather than outputting, for example, a set of characters in database query. What you train your model to output is the series of grammar rules. And so and you create your training data set accordingly. So your model outputs a vector of probabilities, as they always do in discrete cases, but that vector describes not the words you choose or characters you choose, but what is the next rule to evaluate. That's, yeah, and this works really great for anything with structure.
How does like backpropagation or kind of like feeding back work in an example where you use like software like in like strokes? Like, do you have like the example with the drawing?
Mm-hmm.
Like, how do you evaluate? How do you train it? Like, is it just based on examples, or can you kind of like do you have to have examples that it feeds it, or like how does it feed back into the model? Like, how do you?
No, so that is like, no, that's how reinforcement learning works, right? So you have, in reinforcement learning, the whole point of reinforcement learning is that your reward is a black box. So you can backpropagate through your word. So what you do is you run your model once, you produce some random series of strokes. And then, so at the end, so the model just produces something. And then the output is a bitmap, which is the result of those strokes. And then you have a reward function which compares the bitmap, which is pixel by pixel if you want, to the original model is a picture.
Oh, okay, so your goal is to generate, like, to create sort of pictures. Okay, I was like, do you give it to people? Like, how does that, like?
No, so for example, if you want to recreate a Mona Lisa with 3 centimeter thick black brush strokes as well as possible.
Oh, okay.
And so the nice thing about reinforcement learning is you create your own examples. So people often pre-train reinforcement learning models on known data sets because that's easier, but you don't have to. You can start with random and just refine.
Can we just talk about some techniques to make, again, in reinforcement learning context, to make the model less sensitive to the actual reward function? So obviously there's kind of a reward hacking concept where if you misspecify your reward function, you get some weird results. Are there any techniques to make it less likely to overfit specific function use?
Well, I think the trick is to, again, this is an area of active research. There is no single answer. But one thing you could use is try to fit it try to train on multiple rewards. Is one option. The other option is just pre-training on example data sets. So it just starts out in the same space. Yeah, I think those are the biggest ones. And another thing worth mentioning, which is also a bit of a corner of reinforcement learning, but one nice thing you can do is rather than trying to optimize and predict the reward you're going to get, you can try and predict the distribution of rewards that any given action will get. So at each step, rather than just estimating the expected value of your next step, you try to predict the distribution of rewards given each of your next steps. And this gives you more information for choosing the next one. And this could lead to more robust algorithms. But generally, you want to have proximate rewards, and the more the better. And train the model and all of them together. And then, yeah. I guess one thing you could even do is to supply, because again, all these, the networks you use, it's a sliding boundary. So what you could do is you could actually input your reward, rather than just simulating from nothing, you could start simulating from an input vector. And the input vector could record the reward that you're currently optimizing. And this way you could train the same weights for everything, just with different input vectors. But then hopefully information would be shared across the different rewards.
With GAP, we often talk about the generative and the adversarial model being trained together. Do you always do that, or is it worthwhile kind of taking pre-trained adversarial models and, you know, one has hybrid versus fake images, so I can use that pre-trained model with a different iteration model?
Well, I think I would actually do it more the other way around, because the point of the discriminator is that it tries to exploit the weaknesses of a specific generator. So you cannot, well, I don't think it will be very hard to train a useful general discriminator. If anything, I would go the other way, which is you might first want to train a generator using some simpler, more robust ways, like a train generator using an autoencoder, and use this as a starting point. And then you plug in a discriminator to refine it. And I guess the other thing, and again, I know I'm throwing keywords and I'm explaining all over the place, but I'm just hoping that each of those is, again, then possibly half an hour of explanation. But I hope that, if you're interested, please come to me afterwards, or you can just Google them. But one nice trick of stabilizing GANs is a Wasserstein regularization. And this basically means if the space in which your objects live has some kind of a natural metric, for example, L2 distance for images, then by integrating that, you can integrate that metric into how you regularize your models. And that makes the stuff more stable. All right. Well, thank you very much. And please don't hesitate to email me. So I'm egor@mosaicsmartdata.com. So if you want to bounce more ideas on any of this, please drop me a line.